Hello, listeners. In this video, we are going to understand how to derive the mean for a binomial distribution. Now, if you remember that the binomial distribution is denoted by capital B and it follows N and P, right? So N is the number of trials and P here denotes the probability of a success, probability of success, right? In one trial, right? Okay, so if P is the probability of success in one trial, the probability of failure is given by 1 minus P, right? Because in binomial distribution, we are assuming that each trial has got two outcomes. So just as a revision of that concept, trial, each trial has two outcomes. Since there are two outcomes, it's called binomial, right? There are two outcomes. All right. Now, if we are concerned about a particular random variable, a random variable is nothing but a variable which is used in probability, correct? So, of course, it can take real values, but here the random variable x can take values like 0, 1, 2, so on, n minus 1 and n, correct? Because n is the total number of trials. So, there can be a total of 0 successes or 1 successes or maybe n successes. So this n is the maximum number of trials and there could be n successes. So there is success in each of the trials. So the x is a random variable, a random variable. X is a random variable counting 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 the number of successes, right? Success S. Okay, awesome. So now the probability that the value of this random variable x is equal to small x is given by ncx, right? And this denotes the number of ways by which x successes can happen in an experiment with n trials, right? And this is multiplied by p to the power x, which is the collective probability of x successes, and multiplied by 1 minus p whole to the power n minus x, right? So this is the collective probability of n minus x failures. All right. Now, we are going to use this definition in our analysis here. We are going to derive the mean of the probability distribution with this probability mass function. So this p here, we can write this as a p, small p in the bracket x, right? And this would be probability mass function, right? Mass function. This is a distribution function, of course, but since our random variable x is discrete, right? So we are having a finite number of possibilities of the value of x. So this probability distribution function is called the probability mass function. All right. Now you'd see on the top right corner of the screen where I have written down two relations. So the first relation is summation of r is equal to 0 to n ncr multiplied by x to the power r multiplied by 1 minus x whole to the power n minus r is equal to 1. So we are going to use this relation and we are going to use another relation where you see that the r is no longer taking the value 0, but it's the value of r is ranging from 1 to n, right? And instead of ncr in the first equation, let's name this first equation, we are writing ncr minus 1 and the power of x is also r minus 1, and of course like r minus 1 should add up with n minus r plus 1 to give n, right? So these are the few changes, but we are still getting 1, right? So let's say that this is the equation number 2. So we'll be using equation number 1 and equation number 2 in this derivation. All right. So let's now move on to the derivation of the the mean, right? So for that, let's try to write down the definition of the mean. So by definition, mean is equal to mu, and mu is equal to summation of x times p of x, right? Where x ranges from 0 to n. Why 0 to n? Because this counts the number of successes out of n trials. All right. Now what we do is that immediately, as you can see, we have got a px over here. We are going to replace the px with the definition that we have mentioned a little while ago, right? So ncx and then p to the power x and then 1 minus p to the power n minus x, right? So this is the px. And the rest of the things we'll write them as it is. So x here and the summation x is equal to 0 to n. Okay, now what we do is we would want to write down our ncx in a different format. We'll just expand it, right? So this would be n factorial divided by x factorial multiplied by n minus x factorial, right? So this is the representation of ncx, and before that we have got an x, after that we have got p to the power x, and of course 1 minus p whole to the power n minus x. This entire thing is the xth term, right? So the range of x is from 0 to n. So this is what we have. We have essentially rewritten, but instead of ncx, we have used the expansion of ncx. Well, now we notice that there is an x here, which is hanging out there, correct? And we have got an x factorial. So it would be nice if we could write this x factorial as x times x minus 1 factorial, right? And the rest of the things we'll write them as it is. We have got n minus x whole factorial in the denominator. In the numerator, we have got n factorial, right? The x is there out there sitting, and then p to the power x at last 1 minus p whole to the power n minus x. And then this is the xth term again. So summation x is equal to 0 to n, right? Okay, so this is our new expression for the mean, right? Now you can see that we can, very easily, cancel out these two x's. Okay, now once we cancel these two x's, and let's just write it down, right? Because it never harms to write down all the steps. Step jumping is a sin. Okay, anyways, so x minus 1 factorial and n minus x factorial are there in the denominator, n factorial is there in the numerator, and beside that we have got p to the power x 1 minus p whole to the power n minus x. Now you see that the numerator of the term, right, of the summation term is n factorial, whereas the denominator is x minus 1 factorial and n minus x factorial. So it would be nice if we could, get the numerator. If we could get the numerator, right, the numerator factorial, the factorial term of the numerator as equal to x minus 1 plus n minus x, right? Because if we can do that, then we can somehow put that in the something c something format, correct? So that is the idea. So in order to do that, let's write this n over here, this n factorial, as n times n minus 1 factorial, correct? Okay. Now, the rest of the things in this particular fraction, we are going to write them as it is. So x minus 1 factorial, n minus x factorial. So from here, what we'll do is that this n term, right? This n term, we are going to, remove this term, maybe place it somewhere else. Okay. Now, you see that n minus x is there, right? So 1 minus p whole to the power n minus x is the n minus x over here is matching with on the power is matching with the n minus x factorial. Now, it would be nice again if we could somehow match the x minus 1 factorial term, right? The x minus 1 factorial term with the power of p, right? So let's try to do that, right? So we can maybe write p to the power x minus 1, and in order to compensate for the p to the power x, we can write this as p. So p to the power x has been written down as p multiplied by p to the power x minus 1, right? Okay, so far so good. Correct. Then, of course, there is this x is equal to 0 to n, the factorial term, the summation term. And we are done with, like breaking down everything. Now let's clean this thing up, right? And for doing that, what we'll do is that maybe, like this p term over here and this n term here, we'll write this outside the summation. Or maybe, like we can write down np over here in a bracket, right? And then what do we get? We get n minus 1 factorial divided by x minus 1 factorial multiplied by n minus x factorial, p to the power x minus 1, and then 1 minus p whole to the power n minus x, right? And then there is a summation x is equal to 0 to n. Okay, now here, in this step and in the previous step, it is advisable that we do not write n is equal to x is equal to 0, right? Because if we write x is equal to 0, x minus 1 factorial becomes negative 1 factorial, right? So that is not advisable. So we'll change this x is equal to 0 to x is equal to 1. Similarly, in this step as well, correct? Okay. Now, maybe from the previous step as well, we can start doing that, right? From here as well, we'll write x is equal to 1. Before that, it is fine. Okay, great. Now, here you see that the term np, the term in the bracket, is independent of x, right? So if we write down, right, a description for this is independent, independent of x. Right. So since this is independent of x, we can clearly, like write this NP outside. So we'll write NP outside the summation, and then the rest of the summation we'll write as x is equal to 1 to n minus 1 c x minus 1, right? Okay. And then p to the power x minus 1, and then 1 minus p whole to the power n minus 1. Correct. Okay, now you see that like the summation that we have here, the summation that we have here is exactly like our second relation that we had written long back. Correct. So and you see that here this summation is going to be equal to 1, right? Because of the binomial rule. So the answer of the mean is going to be NP, correct? Okay, so why is this 1? Because of the binomial expansion rule, right? And then what we get is NP. That's the answer, which means that the mu or the mean of binomial distribution is equal to NP. And that's exactly what we had to, like prove, right? So hence we end the proof over here. You can pause the video at times to understand the steps. Thank you so much for watching.